Okay, let's do 16.4. Okay, 16.4 is Green's theorem. Okay, so positive orientation of a simple closed curve. Remember, what's a simple curve? It's one that doesn't intersect itself, right? Went over that last time. Okay, curve C. Okay, a positive orientation refers to counterclockwise. Okay, counterclockwise. Okay, think of the right-hand rule. Right hand. How is your right hand curve? Your right hand curves counterclockwise. Okay. Refers to a single counterclockwise transversal of C. Okay, and so let's look at our guy here, and we're going, whoops, bring that guy back. Okay, we're going counterclockwise as we transverse. Okay, traverse. Okay, as we transverse this simple closed curve, where a positive rotation is counterclockwise. Okay, a negative rotation, a negative orientation would be, okay, negative orientation would be clockwise. Okay, and then again, think of the right-hand rule. Okay, as if you took a normal curve to this, okay, it would be normal to this domain. Okay, as we go clockwise, think of it being normal coming up. Okay, what the heck? Why did I stop sharing? Resume my sharing. There we go. Okay, think of it coming up, right? So this is right-hand rule. Okay, so if we had a negative orientation, okay, then it would be going down from D. Okay, so there is a notation such that when we take the integral and we have a circle here, this means that you're integrating the line integral, but you're doing it in a positive direction. Okay, so this is a line integral of positive orientation. That's what that guy means. Okay. Okay, so let's look at Green's theorem here. Okay, let C be a positively oriented, piecewise, smooth, simple closed curve. Piecewise, smooth, simple, closed curve. Okay, it just means everything about this is nice. Okay, closed curve. Simple closed curve in the plane. And let D be the region bounded by C. Okay. Okay, so again, region D, positive orientation. Messing this up. Okay, positive orientation around C, right? C is going to enclose D. Domain D is enclosed by C. And I want to walk around this thing in a positive orientation. Okay, so let that be true. If P and Q have continuous first order partial derivatives on an open region, then on an open region D, then the line integral, positively oriented line integral around C of P dx plus Q dy is equal to the double integral. Ooh, this is interesting. We're turning a line integral into a double integral of area. It's the double integral around D, the area, okay, the domain, which is the area. So the double integral of the partial of Q with respect to X minus the partial of P with respect to Y. Okay, dA. So we can turn a line integral now into a regular double integral. Well, that's nice. Okay, sometimes the line integrals are really hard. Double integrals are a little bit easier. Okay, so let's use this. This is Green's theorem. Okay. So we're going to use Green's theorem to find the double integrals, to find the areas. Okay. Okay. So let's look at number 1 here. Evaluate the line integral, positively oriented, x to the 4th dx plus xy dy. Okay, so where C, let's look at the region C. What's C going from? Okay, where C is the region okay, of these points. C is this region here. Oh, that's not good. It's better. These are points 0, 0, 0, 1, and 1, 1. Okay, so C is this line integral that's positively oriented. Okay, starts at 0, 0 and goes around the figure. We want to take this line integral. Well, instead of taking a 3-piece line integral, 3-piecewise line integral, okay, we can just say, well, that's equal to the difference of the partials. And then we're going to take, with respect to D, a double integral with respect to D here. Okay, so this thing, okay, is going to be the same, going around C, is going to be the same as taking the double integral of D. Okay. of the partials. Okay. Okay, so we're going to say that over this d here, we're going to have d q dx minus d p dy, right? Okay, dA, okay, over d. Okay, interesting, nice. Okay, so the first thing I have to do is find out, well, what's the partial of q with respect to x? Well, what was the original function here? We had x to the fourth dx and xy dy. We wanted the line integral of that. So, well, p is equal to x to the fourth, q is equal to xy. Okay, so the partial of q with respect to x, that's going to be equal to, well, this is going to be y. Okay, so that's y. D p dy, oh, that's 0. Okay, so we're going to say that this is the double integral from y minus 0, okay, dA, okay, over dA. Okay, well, what is dA in this case? Well, it's just this triangle, right? It's just this triangle. So let's do, we've got y there, so let's do dy dx. Okay, we want this, okay, double integral. So we want to know what's y going to go from and then what's x going to go from. Well, what is y going from? Well, y is going from y equals 0 to y equals this line here, which is going to be what? What is that line? I'll highlight that in green. What is this line? What's the equation of that line? Well, it has a y-intercept of 1 and a slope of -1, right? So y equals negative x plus 1. Okay, so 1 minus x and 0. Okay, what does x go from? Well, x goes from 0 to 1. So that goes from 0 to 1. Nice. And so there's my integral. Okay. So let's plug in. So integrate on y, we'll get y squared over 2 from 0 to 1 minus x. Plug in. We get 1 minus x squared over 2. Nice, nice, nice. Okay. Dx, and then we want to integrate that from 0 to 1. Okay. We could pull out the 1/2 if we want. I'm going to square this out. 1 minus 2x plus x squared. Okay. Okay, and then that's all from 0 to 1. So this is 1/2 times x minus x squared plus x cubed over 3. Okay, all of that evaluated from 0 to 1. Okay, so what's this going to be? So this is 1/2 times 1 minus 1 plus 1/3. Ones cancel, and I'm left with 1/6. So what is that equal to? That's the line integral of x to the fourth dx plus xy dy. Okay, over C, which is this isosceles triangle. So that's the line integral over that. Okay, so again, instead of having to do three pieces here or trying to find some way to parameterize this thing, okay, we can just use Green's theorem and go directly to, okay, a double integral. So that's the power of this thing. Okay, number 2. Let me go back to red. Number 2. Evaluate positive orientation around C of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy. Okay, nice, nice, nice. Okay, so what do we want? Oh, and it's around the unit circle. No, it's not the unit circle. I lied. Around the circle of radius 3. It's x squared plus y squared equals 9. Okay, so we're going to go around this circle positively. Right, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oops. Okay, so we'll go around the circle. Okay, go around the circle. Positive orientation. Okay, positive orientation here. And so we're gonna, instead of doing the line integral around this thing, which this thing would be pretty complicated to do, the line integral around this thing, we're gonna do a double integral, make it a little less complicated. Okay. So we're gonna say that this thing is gonna be dq dx minus dp dy. Okay, double integral around d, that's the area of that circle. Okay, dA. Okay, so what is q? Q is this thing. Oh, sorry, what is q? Q is this thing here. So dq dx is going to be equal to the partial derivative of this with respect to x. Well, the only thing that survives is the 7. That's nice. Okay, what's the partial with respect to y of p? Well, the only thing that survives over here with respect to y is 3. So this thing becomes d3 7 minus 3 dA. So this thing is d4 dA. Okay, so now I want to change this to rectangular coordinates. This is 4 dA is going to be dy dx, except this is the circle. So I might want to change to polar coordinates at this point. So let's change it to polar coordinates. So we're going to go 4r dr d theta, where r goes from 0 to 3, and theta goes from 0 to 2 pi. Okay, so this is going to be 2r squared from 0 to 3. So that's going to be 18. Okay, and then 0 to 2 pi d theta is just going to be 18 theta from 0 to 2 pi, and plug that in, I'm going to get 36 pi. And that is the, okay. Okay, that is the line integral of that guy there. Okay. Okay, so the area of a region D can be computed using Green's theorem where dq dx minus dp dy is equal to 1. if I let that equal 1, okay, so thus, what we're saying is that the double integral of 1 dA is just equal to A. Okay. Okay, there are special relationships where dq dx minus dp dy, okay, is equal to 1. But among these are, okay, when dq dx is equal to 1 and dp dy is 0. So if you were to do a what partial would you give you 1 if it was just, if you're focused on the x's, that would just be x, right? So we could say that among these are the line integral of x dy. Okay, because why? Because this is right. So in this case, dq dx is equal to 1, and dp dy is equal to 0, right? So, right. Okay. Also, y dx, right? Okay, actually it's not. It's negative y dx. Okay. And why is that? Because when we take the, if we were to take the partial, okay, in this case, dq dx would be 0, and dp dy would equal negative 1. Yeah, negative 1. So we got 0 minus negative 1 equals 1. Okay, negative 1. Okay. And, okay, if I take 1/2 of 1 plus 1, if I take 1/2 of 1 plus 1, I get 1 as well. So this would be x dy minus y dx. Since this gives me 1, this gives me 1. If I add them together and take 1/2 of it, then that should give me 1 as well. Okay, so these are the three relationships. Okay, this would be where I would do, since dq dx equals 1 and dp dy equals negative 1, then you get 1 minus negative 1, which is equal to 2 over 2, which is 1. So it all comes out to 1 in the end. Okay, so once again, these are the three relationships. And there are more, because, you know, there's an infinite combinations that you can get 1 here, especially if you're dealing with constants, you know, or coefficients or anything like that. Okay, but among the basics, these are the basics, are these. Okay. So how does that help me? Well, let's use this to find an area. Okay. So 3. Find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Okay. So let's positively orient this thing. Okay, let's say that we have some sort of ellipse. That was a bad ellipse. Okay, and it's positively oriented. Right, C, and we want to know what's the area of D. Okay, so I'm going to say that this is going to be 1 dA over D. Okay. And I'm going to say that this is equal to, okay, the line integral of x dy minus y dx. Okay, I'm going to say that's equal to the line integral, or the integral, okay, the positively oriented integral of this thing. So I'm going backwards. Okay, so let's parameterize this function here. Okay, if I had an ellipse, okay, and I wanted to find a point on that ellipse, okay, so a point on this ellipse would be, if I let the major axis be A and the minor axis be B, then this would be A cosine t, B sine t. Okay, so that's what my x and y would be equal to. Okay, so x would be equal to A cosine t, and y would equal to B sine t. So what would dx be equal to? Well, that would just be negative A sine t. Okay, and then what would dy be? Well, dy would just be B cosine t. Okay, so now if I were to multiply these together, right, x and dy, okay, that would be this guy here. If I multiply y dx, that would just be this guy there. Okay, so let's say that we've got 1/2, okay, positively oriented integral of A cosine t times B cosine t, right, minus, okay, y, which is B sine t, oh, this should be A, I'm sorry, minus A. Okay, B sine t times negative A, I'll put some parentheses here. Okay, negative A sine t. Okay, so, and we'll do a dt here. And what is the limits of integration on t here? Well, t is now an angle, right? It's an angle, and the angle is going to go all the way around the ellipse from 0 to 2 pi. So this is 0 to 2 pi. Okay, positively oriented, 0 to 2 pi. Okay. So then this just becomes 1/2 times the integral of 0 to 2 pi of AB cosine squared t plus AB sine squared t dt. Okay. So this is 1/2 0 to 2 pi of AB times cosine squared t plus sine squared t dt. Okay, so I could turn this guy into 1. That's just equal to 1. And so we just get 1/2 0 to 2 pi of AB dt. Okay, so let's integrate that. Well, that's just ABT from 0 to 2 pi, 1/2. Plug in the 2 pi, and the 2's are going to cancel out. But let's do that. 1/2 times AB I'll just do 2 pi AB. Okay, minus 1/2 times 2 pi, or 0 AB, sorry. That goes to 0. The 2's cancel out, and I'm left with pi AB. Okay. Does this make sense? Well, what if A equals B? Then what do we have? If A equals B, don't we have a circle? Right? If A is equal to B, then we just call that R. And so what would be the area of my circle? Wouldn't it be pi R squared? Oh, yeah. Okay. Okay, that's 16.4. We will cover 16.5 in a week from today. Okay, there is no school on Wednesday. You can thank your fellow veteran for that. Thank someone who served in the military that gave you the right to go to school for free in this country. It's pretty nice. Yeah. Okay, I will. I'll see you guys next Monday.
Professor Holtman,
Yes.
can you actually help explain one of the questions in the homework?
Sure.
I have it right here. It's this chapter. The question is evaluate the integral by the two following